Welcome to the second month of AOA. This month, we will be covering searching and sorting algorithms. This slide is an overview of what we will be covering today, so feel free to pause if you want to go over it before we move on to the next slide.
All right, so starting with a brief overview. So, searching is pretty self explanatory. It is finding the item or object that you want in a certain data structure, and sorting is putting all the items in a certain order. So, we often perform these tasks everywhere, um, especially searching because we are always needing to retrieve certain data, and sorting because it makes certain searching algorithms easier, such as decreasing the amount of time it takes for searching algorithms, but we'll talk about that later. And specifically for today, we'll mostly be dealing with arrays, but these are also applicable to things like array list, etc. Although maybe not every single one will work for every single data structure.
Let's now talk about searching algorithms. So there's two main types of search algorithms. The first is linear search, which can be performed on any type of array. So all linear search does is it starts at the first element of the array and it goes through each element one by one until the item is found or until the entire array has been checked, which means that the item is not found. The second search algorithm is binary search. So binary search requires an array that is already sorted, but what it does is it starts at the middle and checks to see if the value is greater than or less than the initial value. If it's equal, then the item is found. If it's less, it cuts the search interval down to the lower half, so it reduces the amount of searches required by half, and you rinse and repeat until you find the item. And the same principle works for if the value is greater.
So, for the implementation of searching algorithms, if you're performing a linear search, you can just use a for loop or a while loop to go through the array and see if that index is what you found, then you can mark true and just quit, or else you can increment the array variable by one and then keep looking. And obviously, you'll stop if you reach the end of the array. So I can take analysis of search algorithms, and here we'll just talk about how efficient each search algorithm is. So linear search goes through every single element, which obviously means that as every single element in your array list is searched or array, then it'll take O of n time because it goes through every single element one time. Whereas binary search has a much better time efficiency, being O of log n, because it is able to cut the array in half every single time it goes. So that means that if you can, use a pre-sorted array because then you can use binary search and cut the search time by a significant amount. So, for example, if you're using a dictionary and you want to search for a specific word, you can use linear search, but that would be really slow because you have to go through the entire dictionary. Instead, if we find the letter that the word starts with and go from there, then we can cut out like 25, 26 of the entire dictionary, which is similar to how binary search works.
Now let's move on to sorting algorithms. The first sorting algorithm that we will go over is bubble sort. So all that bubble sort does is it checks to see if two adjacent values are in order. If not, they will swap indices, and you keep repeating this process until it gets to the end of the array, and it will go over and over again until no more switches have been made in any given pass. Once no more switches have been completed, that means that the array is sorted. We call this bubble sort because in this visual right here, we see how the highest value will eventually float to the top. And now on to the implementation. Here we use an integer variable called temp, or just like a temporary variable. This is very common in sorting algorithms when we need to temporarily store a variable somewhere, so that way we can put it in a different array index.
So now for insertion sort. This is probably the one of the simpler sorting algorithms and probably an intuitive one that you can think of off the top of your head. So you'll first examine the two first values in the array, and if they're in the order, then you swap them. If they're in the right order, then you do nothing. Then you look at the next value, or the next two pairs of values. Then you swap those in the correct order relative to the first two. So if you had 4 and 3 as your first two values, you'd swap it to be 3 and 4. And then if you have 2 after that, you'd put 2 at the very beginning. So in the diagram, it shows 2 jumping straight to the front, but in reality, when you implement insertion sort, you need to swap 2 first with the index 1 and then with index 0. So that's a two-step process. And you repeat adding a new value to the sorted pile until you reach the end of the array. So for implementation, it'll loop through the entire array, starting at the first one, and you'll just compare pairs. And if you find a pair that's not in the right order, then you'll swap them, and then you'll have to go back one step because you might need to swap it again for the number to reach the correct place in the array.
The next sorting algorithm that we have is selection sort. Selection sort works somewhat similarly to insertion sort, but it's different in the sense that you first identify the lowest value in the entire array and move that to position 0. You repeat that over and over again by finding the next smallest value in the array until you sort the entire array. So here in the implementation, we start by creating a for loop, and then we just end up looping through the entire array. And right here we have our variable min index, and the minimum index increases every time we sort another element.
Okay, and now for merge sort. Merge sort is a more complicated way to sort arrays, but it's actually more efficient than the methods that we've examined before. So you'll start with an array and you'll split it across the middle. Now, if there are an odd number of numbers in the array list, doesn't really matter. You can add the middle number to either one of your arrays. And you'll keep doing this until the numbers are either by themselves or in pairs with another number. Next, you'll take those numbers and split them up further so that every single number is by itself. And then you'll start recombining. So you'll recombine them in the correct order, and this is really easy to do by just using a simple if statement. And after you do this for every single layer of the array, then the final layer will come out to be the correct sorted array. And as for the implementation, since the actual code would be too long to write on the screen, I've just put in the pseudocode, which is probably easier to understand anyways. So once you start, you'll declare the beginning bound of the array, the right bound of the array, and the middle value of the array. And then you'll perform a merge function so that if the value to the left is greater than the value to the right, then you'll return because then it's already correct. But then if it's not, then you'll find that the middle is in between the two values. You'll merge it such that you make two different arrays, and then you can sort those arrays individually and then merge them all at the end. And then after all of that is completed for every single layer, then you stop.
Much like merge sort, quicksort is another somewhat more complicated sorting algorithm, but as its name implies, it's also quite fast and efficient. Quicksort relies on an element known as the pivot. The pivot is an arbitrary value, but generally when quicksort is implemented, we choose the first value in the array as the arbitrary pivot. Elements are then swapped around such that all of the elements less than the pivot go to the left and all elements greater go to the right. This process is done over and over again with each subset until all of the elements are sorted. So in the implementation, we first see that we declare the pivot to be the first element in the array. And then we keep creating sub arrays by selecting pivots within each pile. And we see that this is a recursive algorithm just like merge sort, because we repeat this process over and over again until everything is sorted.
So now that we've gone through a whole list of sorting algorithms, it's okay if you can't implement any of these off the top of your head, but it's best to just know the overall picture of how they work. And the reason is that different sorting algorithms will run at different times, and some are better than others. So if we look at the first sorting algorithm, we can see that merge sort has an n log n best case, n log n worst case, and n log n average case, with a space complexity of O of n. That's different from insertion sort, which is going to be the same as bubble sort but different from quick sort. And so it's important to use this graph to understand which sorting algorithm might be best for you. So if you're looking at just time, then clearly merge sort would be the winner here because it has n log n for every single run case, but never does it reach n squared. And that might be great if you have unlimited computing resources or computer storage, but you can see that its space complexity is really large. Compare that to insertion sort or bubble sort, where you don't require any new memory and you only use the array itself when you're doing the sorting. So even though one sorting algorithm might be better in some ways, it might be worse in other ways. So it's best to just keep that in mind.
That's all that we have today for searching and sorting algorithms. Stay tuned for next month where we will be introducing divide and conquer programming.